Plasma, from ancient Greek by lambda sigma mu alpha comma meaning moldable substance 1, is one of the four fundamental states of matter, and was first described by chemist Irving Langmuir II, in the 1920s. 3. It consists of a gas of ions, atoms which have some of their orbital electrons removed, and free electrons. Plasma can be artificially generated by heating or subjecting a neutral gas to a strong electromagnetic field to the point where an ionized gaseous substance becomes increasingly electrically conductive. The resulting charged ions and electrons become influenced by long-range electromagnetic fields, making the plasma dynamics more sensitive to these fields than a neutral gas. 4. Plasma may be the most abundant form of ordinary matter in the universe. 12. Although this hypothesis is currently tentative based on the existence and unknown properties of dark matter. Plasma is mostly associated with stars, extending to the rarefied intracluster medium and possibly the intergalactic regions. 13. The word plasma comes from ancient Greek by lambda sigma mu alpha comma meaning moldable substance 1, or jelly, 2, and describes the behavior of the ionized atomic nuclei and the electrons within the surrounding region of the plasma. Very simply, each of these nuclei are suspended in a movable sea of electrons. Plasma was first identified in a Crookes tube, and so described by Sir William Crookes in 1879, he called it radiant matter. 14. The nature of this cathode ray matter was subsequently identified by British physicist Sir J. J. Thomson in 1897. 15. The term plasma was introduced as a description of ionized gas by Irving Langmuir in 1928. 16. Louis Tonks and Harold Mott Smith, both of whom worked with Irving Langmuir in the 1920s, recall that Langmuir first used the word plasma in analogy with blood. 1718. Mott Smith recalls, in particular, that the transport of electrons from thermionic filaments reminded Langmuir of the way blood plasma carries red and white corpuscles and germs. 19. Langmuir described the plasma he observed as follows. Except near the electrodes, where there are sheaths containing very few electrons, the ionized gas contains ions and electrons in about equal numbers so that the resultant space charge is very small. We shall use the name plasma to describe this region containing balanced charges of ions and electrons. 16. Plasma is a state of matter in which an ionized gaseous substance becomes highly electrically conductive to the point that long-range electric and magnetic fields dominate the behavior of the matter. 21-22. The plasma state can be contrasted with the other states, solid, liquid, and gas. Particles, that is the overall charge of a plasma is roughly zero. Although these particles are unbound, they are not free in the sense of not experiencing forces. Moving charged particles generate an electric current within a magnetic field, and any movement of a charged plasma particle affects and is affected by the fields created by the other charges. In turn, this governs collective behavior with many degrees of variation. 1023. Three factors define a plasma. 24-25. The plasma approximation. The plasma approximation applies when the plasma parameter, lambda, 26, representing the number of charge carriers within a sphere, called the Debye sphere whose radius is the Debye screening length, surrounding a given charged particle, is sufficiently high as to shield the electrostatic influence of the particle outside of the sphere. 21-22. Bulk interactions. The Debye screening length, defined above, is short compared to the physical size of the plasma. This criterion means that interactions in the bulk of the plasma are more important than those at its edges, where boundary effects may take place. When this criterion is satisfied, the plasma is quasi-neutral. 27. Plasma frequency. The electron plasma frequency, measuring plasma oscillations of the electrons, is large compared to the electron-neutral collision frequency, measuring frequency of collisions between electrons and neutral particles. When this condition is valid, electrostatic interactions dominate over the processes of ordinary gas kinetics. 28. Plasma temperature is commonly measured in Kelvin or electron volts and is, informally, a measure of the thermal kinetic energy per particle. High temperatures are usually needed to sustain ionization, which is a defining feature of a plasma. The degree of plasma ionization is determined by the electron temperature relative to the ionization energy, and more weakly by the density, in a relationship called the Saha equation. At low temperatures, ions and electrons tend to recombine into bound states, atoms 29, and the plasma will eventually become a gas. In most cases the electrons are close enough to thermal equilibrium that their temperature is relatively well defined. This is true even when there is a significant deviation from the Maxwellian energy distribution function, for example, due to UV radiation, energetic particles, or strong electric fields. Because of the large difference in mass, the electrons come to thermodynamic equilibrium amongst themselves much faster than they come into equilibrium with the ions or neutral atoms. For this reason, the ion temperature may be very different from, usually lower than, the electron temperature. This is especially common in weakly ionized technological plasmas, where the ions are often near the ambient temperature. Since plasmas are very good electrical conductors, electric potentials play an important role. Clarification needed: the average potential in the space between charged particles, independent of how it can be measured, is called the plasma potential, or the space potential. If an electrode is inserted into a plasma, its potential will generally lie considerably below the plasma potential due to what is termed a Debye sheath. The good electrical conductivity of plasmas makes their electric fields very small. This results in the important concept of quasi-neutrality, which says the density of negative charges is approximately equal to the density of positive charges over large volumes of the plasma. \display style n sub e equals \lang l z \reng len sub I, n underscore e equals \lang l z \reng len underscore I, but on the scale of the Debye length there can be charge imbalance. In the special case that double layers are formed, the charge